Um, am I audible to everyone? Okay. So I am Abhishek, and this is supposed to be me accurate up to my ability. So not so accurate. And so I'm going to talk about the relationship between statistics and optimization and my work area in general. So today I'll first briefly give an overview, like a very high level overview on what I work on. And then I'll talk about my most recent work, which got accepted in this year's New Rips. And then I will spend some time on my future works, future directions. So let us start. I have, so my research, in research, I have two hats that I wear. So one is the optimization. So I work heavily on optimization. And at the same time, I have another one where I wear the hat of statistician. So I mostly work on optimization problems, which appears in statistics, right? So it's now known fairly that, yeah. So it's now fairly known that there is a very close relationship between statistics and optimization, and there are, as you can see, there are standard statistical problems like linear regression and Hoover regression, and like all of these problems. So they all involve optimization over some space. So it can be a convex optimization, it can be a non-convex optimization. For example, here, if you look at even causal learning, these can be formed as an optimization problem over DAGs, for example, or as you will see that instrumental variable regression, which is a common technique for causal learning, that can also be formulated as conditional stochastic optimization. And that I will talk about today. And then, of course, like non-parametric regression, you can look at it as optimization in the function space and so on, right? Now, in very briefly, if I just focus on, it's a very crude approximation of these two fields. So in statistics, mostly we are interested to learn data complexity. So what I mean by that, let's say I have a learning problem. It can be regression, it can be classification. Mostly we are interested to know how much data do we need to learn some particular parameter, right, or particular system. Whereas in optimization, we are mostly interested to learn the iteration complexity. That means if I have an iterative algorithm to solve any optimization problem, how many iterations do I need till it converges, right? And in statistics, inference is, of course, a huge part because you want to know the uncertainty about the estimate that you have made. And you have asymptotics for that. We have CLT type of results. We have covariance estimation, hypothesis testing. Everything I am like trying to bring them under this one umbrella of inference. Okay. And optimization, on the other hand, is more like a tool to solve statistical problems. And not only statistical problems, it's applicable for a much wider class of problems. For example, in operation research, for example, right? It's used heavily. Now, if it seems like they are really disconnected apart from the fact that optimization is just a tool, but there is a common area where at least we can match the first two requirements, data complexity and iteration complexity. So in this common area, what we have is the learning with streaming data or online optimization setting. So what I mean by that is that, like in statistics, we come across streaming data all the time, but in optimization also, you can do online learning where you obtain one data point at each time point, and you just update your optimization parameters or optimization algorithm based on that one data point that you have received, right? So in this case, if I can establish an iteration complexity that's exactly equal to the number of data points that I have, so these two complexities are the same, okay? So majority of my work belongs to this common area, but the other predominant area that I have worked on is in here, because in optimization, we are using these algorithms to estimate the parameters of some underlying problem, be it regression or classification. but there hardly ever we talk about inference, right? Because inference is it really belongs to statistics, and here like purely optimization literature will just talk about convergence. Okay, so we need to talk about inference as well. Okay, so my work belongs to these two areas where I have worked on inference for stochastic optimization estimators that I will come to towards the end. And other part is establishing iteration complexity for various optimization setups. Okay. So in today's talk, I will start with my most recent work, which is on stochastic optimization algorithms for instrumental variable regressions with streaming data. As you can see here again, we are in the streaming data scenario. So data complexity will be equal to iteration complexity. And then I'll spend some time on future directions, I'll discuss some areas that I'm thinking about. Okay, so let me start with this part, the first part of my talk. So what is instrumental variable regression? What's the motivation, right? So in typical linear regression, what we have is something like this, that you have a feature, you have a response, and there is an error. And this feature and error, they are uncorrelated. And you are trying to regress y on x, right? But it may happen that we have a scenario where this feature is also correlated with the error, okay? And it can happen because of error in variables, because of unobserved confounders, and so on. And if you want to understand to an example, let's say I am trying to understand what effect years of schooling, that is how many years you have spent at school, how does that affect the earnings that I'll be earning in like after I graduate, right? Now, there are few things which are not measurable. For example, how much motivated I was or what ability I had. So it is kind of expected that the more ability a student has, it's more likely that they will follow more years at they will spend more years at school. At the same time, if you have more ability, there is higher chance that you'll be earning more. Okay. And so again, how much motivated you are. So these are the things which is difficult to measure, right? But they exist and they affect both of them, both the feature and the response. If you want to think about it in terms of causal inference, so these are the unmeasured or unobserved confounders, which is affecting both, right? Now, question is, how do you estimate the effect of x on y? Okay, so here comes instrumental variable regression, and of course, in causal learning there are numerous methods to do it, but we are focusing on this method. So where I assume that there is another variable z, which is correlated with the feature, but uncorrelated with the error. Okay, and it only affects the response via x. So there is no direct, as you can see, that there is no direct connection, direct correlation between z and y. It's only through x that z affects y, and z and epsilon are uncorrelated. Okay, so this is instrumental variable. In our example, it could be distance to college. So distance to college technically shouldn't affect your earnings, but it is more likely that you will attend a school if it's like, let's say you are living in the middle of Sahara. Then of course there is no college or school near to you, and there is like maybe you will attend some school or college for a few years, but eventually you will drop out because it's so hard to keep that up, right? So distance to college can be taken as our instrument. Now, a good instrument will have these properties. That is, it should be highly correlated with x. In a minute, we'll see y. And it should be independent of epsilon, which is called exogeneity property. And this is like really crucial. The first two are really crucial. And then the last one, which is it affects y only through x. Okay. So these are the properties of a good instrument. All right. So now if I write it as a model, so let's say this is what the model looks like. So y is some function of x, which is parameterized by theta, and theta star is the optimal parameter. That's the data generating mechanism. And let's say x is dependent on z through some function h, which is parameterized by gamma star. Okay. And epsilon1 and epsilon2, they are correlated. And that actually introduces the correlation between x and y, sorry, x and epsilon. But at the same time, z is independent of both of this. Okay. So z is independent of epsilon2 and epsilon1. So this is the setup that we will be considering. And what's our goal? Our goal is to learn this causal parameter. That is, our goal is to learn just theta star, right? What? Yes.
Condition on x, epsilon and z becomes dependent. Because that
Conditioned on x.
Z structure in this
Conditioned on x, which depends become?
z and epsilon. Z and epsilon.
But why? Yes, that's true. But why would you like? No, like what's the? That's true, but
so that comes from the property of the tag. So if z,
that is true. But what's the question?
so is that z and epsilon is independent, or
Z and epsilon is independent. That's so. I mean, z and epsilon 1 and z and epsilon 2 are independent. Yeah, yeah. So this is there. So there is another epsilon 1 which is for this relation. Yeah, yeah. So epsilon 2. Sorry. Yeah. Okay. So all right. So if we want to estimate theta star with streaming data. So we don't have, because in the offline setting it's fairly known how to do it, but streaming data will throw some more challenges in this setting, and we will see in a minute why. But this is a problem setup, and this is our goal. Okay. So traditionally, you do it by a two-stage method. Let's say in the offline setting, when we have all the data with us, so you can do a two-stage method. So in the first stage, what you do is you estimate this x on z. So you just get the condition. Let's say I have a very good model and I can learn this. So what I learn is x hat, which is the conditional expectation of x given z. And then in the next stage, instead of using x as our predictor, we use this conditional expectation of x given z as our predictor for y hat, for y. Okay. So why does that help? Because expectation of x given z, this is like really conditional on z. This is a function of z. So it removes all the effect of x. So this is kind of independent of epsilon 1, and then that uncorrelated. So then we can just go ahead with our normal regression setup, and we can just use this x hat as our predictor and get y hat. Okay. So using z, we are kind of deleting, or we are kind of destroying this correlation, and we are estimating y hat. Okay. So this is the traditional two-stage method. But there is a weakness here. The weakness is, like, even in the offline setup, the weakness exists. The weakness is that, okay, sorry. So if it was if it was linear model, so it would x hat would look something like this, and then you can use x hat. Okay. So but the problem is that if you do not know what the relationship between x and z is, and there is often a chance of model misspecification. Okay. And if that happens, then of course that leads to severe, like severely bad performance in the second stage. And at the same time, if I won't get into the details of that, but if the first level is not really a linear setup, you are using some logistic regression instead of just squared loss, you are using some logistic regression or some probit loss, then of course this method is again biased. You can show that this is biased and it doesn't work. Okay. So this is a problem even in the offline setup. All right. So now if I look at it from optimization point of view, you can formulate the same problem in this manner. Okay. So it is an optimization problem over the joint density of y and z, and the inside is just y minus expectation of x given z of gx, and this g function is what we are optimizing. Okay. Now, this why does this help? So why does this at all solve our problem? First, let us see that. Okay. So the advantage of this, it will be clear in a moment, but advantage of this is that we are not using any explicit model for X and Z. So there is no question of me specifying X and Z model. Okay, so I'll just solve this problem directly on G. So we are not explicitly modeling this X and Z. So we are directly solving this G. And let's say for now that I can solve this problem very efficiently. So if I can do that, then of course we don't need this, and there is no risk of me specifying XZ model. All right. Let's see what happens in the linear case. All right. So when the true model, let's say between Y and X is linear, and X might be non-linear, it doesn't matter. So it can be, let's say, some H gamma star Z. It is just like before, but Y is linear model. Okay. So in this scenario, what is expectation of X given Z? That is just theta times H gamma star. And so here G theta is just the linear class because we are assuming itself to be a linear model. So this is just a linear class of functions. So this is theta times X. And if I just take the expectation, this is just theta H gamma star Z. Okay. Now, if I plug in this estimate over here, this is what the loss function looks like. Okay. Over the joint densities of Y and Z, this is the final expression that we get. And then there are some terms which are independent of theta. So when is this term minimized? This term is minimized when theta is equal to theta star. Okay, and that's exactly what we are looking for. So at least in the linear case, this makes sense. All right. So any question here? Okay. So if not, so in the non-linear case, that also makes sense. Why? Because let's say this is the objective that we are trying to solve. Now this one, we are denoting it as just HGZ. So this, of course, this term over here depends on this function G and Z, and not on X because we are conditioning on Z, right? So this is some HGZ, and if I rewrite it, it turns out to be like this. Okay. Now, since we are minimizing squared loss, it's exactly when is this minimized? This is minimized when expectation of Y given Z is the orthogonal projection. So this conditional expectation is basically the orthogonal projection minimizing the L2 distance between Y and Z. So if this has to be minimized, so HGZ should be this equal to this expectation of Y given Z. Okay. And the corresponding G turns out to be the solution. And that's exactly what happened in our previous case. So this is what we got. And then if you expand it, you will get theta minus theta star. So in this case, because it's linear, you can just see it appearing here that theta becomes theta star. And since, oops, in the nonlinear case, so you just have to figure out what G this corresponds to, and that gives you your expectation of Y given Z. Okay. So even in the nonlinear case, this makes sense. So, yeah.
So, how are you going to then find that G? Because to find the G which leads to HG star to be the conditional mean of Y given Z, you still need to know something about the distribution of X given Z. Right?
Yes, that's true. So that's why we don't need to, we won't be solving this. We will be just So since we'll be using the stochastic optimization algorithm in a minute, so we won't be modeling this expectation explicitly. So what we will assume that we have data from this distribution and we'll just directly optimize over G. So it's not that we are going to evaluate this over some n data points collected from X and Z and then optimize that function. But it's just we are assuming that we are optimizing G, or like assuming access to data from X and Z distribution.
Okay, but when you do that, what are you assuming about? I mean, so are you then non-parametrically estimating?
Yes, for general, yeah. So for general class of functions, you have to do non-parametrics, but we'll parameterize it and we'll assume that there is some it's parameterized by theta and it belongs to some non-convex or convex, like it's smooth enough and everything. So, and then we can just directly optimize over this one. So, but if you are not parameterizing G, then of course you have to be able to do it in the function space. All right. So now, what are the challenges here? So firstly, this optimization involves this inner expectation, which again, like this is exactly related to that we do not know that what this expectation is, firstly. And we don't have any closed form because we are not assuming anything about the model. And we are assuming streaming data. So it's not even possible that we will just, like we will wait for some time, we'll get some data and then make some, like finite sample approximation of this expectation and just go ahead with that. So that's not permissible either, okay? So this optimization itself is not very friendly, right? So here, let's try to like optimize, let's try to parameterize G. So this is exactly what Oliver mentioned, that we will parameterize G by theta and we'll optimize over theta. Now, natural question could be that why don't we use something like gradient descent or like stochastic gradient descent to solve this minimization problem? So what I mean by that is just treat this, forget about this explicit expression, treat this as a function that you want to optimize over theta. So if you are doing gradient descent or SGD, so this is what the update will look like. So at any point of time, you are updating your parameters, theta t plus 1, based on theta t minus some step size, times the gradient of the function evaluated just at this sample, okay? Because we do not know the expectation, we don't even try to do that. We just evaluate the gradient at this sample WT, okay? And WT, of course, is just xt, yt, zt, which is IIT, okay? But now, if we take a closer look at what this gradient is going to be, so this is what you get, okay? So this is the gradient, because this is the expected version. And since we have the streaming data, and we do not know what the expectations are, what the distributions are. So we just, instead of evaluating this expectation, we just plug in whatever estimate we have. So instead of taking the expectation over X, we just take XT. Here we just take YT. Here we just take, again, XT, okay? But this doesn't work because it has a severe problem, which is this gradient over here, this is biased, okay? So in SGD, you have to do either of you have to show either of two things. Firstly, you have to show that the gradient estimator is unbiased. That leads to nice solutions. Or at least you have to show that there is bias, but the bias decreases over time. Neither of those are true in this particular case, okay? So what do? So we change our data collection system. So what we do is at every time point, instead of sampling one xt from this probability of x given zt, like distribution of x given zt, we sample two, okay? And this xt and xt prime is independent of each other, okay? Now, you can of course say that this is not a streaming algorithm because you are accessing two data points at each point of time, and that's true, that this is not purely streaming algorithm. And later on I will show an example where we are in the purely streaming setup. But for now, let's say this is permissible, that at every point of time I'm getting one sample of like zt, yt, but for xt we are getting two independent copies from this probability distribution, okay? So if you are this is kind of like data splitting, but in an online setup, in a streaming setup, okay? So here I will modify my estimator, where inside it will just be xt, but the outside term I will just evaluate on xt prime, okay? So this kind of makes these two things independent. So this one and this one, they becomes independent of each other, conditioned on theta t, of course. So they become independent of each other. So now if you evaluate the gradient, you will see that this turns out to be unbiased, okay? And that's all good. So then this is the algorithm that we will turn up with. So this is like exactly stochastic gradient descent, but our gradient estimator is evaluated over two independent samples, xt and xt prime, okay? So for this particular setup, there are some assumptions. These are fairly like standard in instrumental variable regression. So this is on IID, and it assumes some regularity conditions on the covariance matrix. So I don't think I have time to go over all this in details. So I'll directly go to the convergence result. Okay. So this is what we can show, that the convergence rate of the expected convergence rate of theta t to theta star is of the order 1/t. And the step size that you have to choose is kind of the order log t over mu t. Okay. But again, like as we said, that this is very nice, but at the same time, this is not purely streaming setup. We are accessing two, like one ZT and YT, but two copies of XT. So can we do anything in the purely streaming setup? And we can do so for the linear model. Okay. So what I mean by that is now our model looks something like this. And again, the correlations remain same, that X is correlated with epsilon1, epsilon2, Z is not correlated with either of them. Okay. So in this particular setup, we have to jointly learn theta and gamma, because we are, so here, so this is the difference. So in the previous one, we avoided modeling the relationship between X and Z completely, which removed the chance of or risk of model misspecification, but we needed two samples. Here, we have one sample. We will access one sample at a time, but we are modeling this X to be linear here. And actually, you can take this, so you can make this part non-linear, so that even then it works, but this part has to be linear, okay? And then we can jointly learn, and then of course we have to jointly learn theta and gamma, because we are also parameterizing this part, all right? So from gamma's perspective, the optimization looks something like this, that it's just like a normal, like regression, like least square regression. And the gamma t update, if I just want to solve it using SGD, just like we did before, this is what it looks like. And from theta's perspective, it looks something like this. Okay. So this is just the estimator that we had before. I'm just plugging in the linear evaluation of that, and this is what we turn up with. Okay. But what's the issue? The issue is that we do not have xt prime anymore, because we are just accessing one sample at a time. So if we do not have xt prime and we just replace it by xt, so then it is biased, right? As we have seen before. So what do we do, right? So the fix is that we replace this xt, the outer xt, with gamma star transpose ct, okay? And if, let's say we know gamma star, so, and I'm doing this, now let's see what happens to the gradient estimator. And it turns out that this is actually unbiased, okay? So this is all good, but at the same time, there's no bias, but at the same time, gamma star is unknown, okay? So if gamma star is unknown, what can we do? Because we are learning gamma star by gamma t updates. So why don't we just replace this outer gamma star by gamma t? But that will again introduce bias, because we do not know the exact model. But what's the good news? The good news is we are learning gamma star by gamma t updates. So the bias is kind of proportional to this error term over here, and this becomes small over time, so we can control the bias. Okay. All right. So now this is the update that we are using, and it sounds like it's all good and it should work. And if I implement it for a very simple linear model, this is the performance that we get, that the iterates diverge pretty fast. Okay. We constructed the algorithm in a very logical manner, but still it diverged. Okay. So where did we go wrong? Now, this is a little bit technical. So what actually happens is, if you roll out the iteration of theta t, you will have some qt hat matrix. And since there is gamma t outside and gamma star inside, because xt depends on gamma star, not gamma t, so the qt hat matrix turns out to be something like this. And this matrix over here, this can be negative semi-definite, okay, or negative definite even, depending on your initialization. Okay, so this matrix can be, and if this is not, this particular thing is not small, like the maximum eigenvalue is not smaller than 1. This is basically not a contraction, and since it's not a contraction, the iterates can diverge. Okay, so what do? We replace the inside xt, which was here, by gamma t zt as well. Okay. So if we do that, then what happens is this qt hat matrix is just now gamma t zt transpose gamma t. So this is at least positive semi-definite. Okay, it might be zero, it may not be an exact contraction, but this is still positive semi-definite. So it doesn't diverge at least. Okay, so this should work, it seems like, and this gives us our actual algorithm which we are going to use. So which is of this form, and here as you see that the inside xt is also replaced by this one. Now let's see if it actually works. So this is the comparison between these two updates, the update we saw before, and this is the final update. And as you can see, so here in this region, so this is negative semi-definite, and gamma t minus gamma star is large because we haven't learned about gamma star yet. So it diverges. But once this error becomes small, this term is very close to gamma star times gamma star, which is greater than equal to 0, and this kind of starts converging. Okay, but by the time it starts converging, the error has become, so this is log 10 base, so the error has become pretty large. Okay, so whereas our final update, it kind of stays very close because of bad initialization, but at the same time, it starts diverging kind of around the same time. But since it hasn't diverged by like 10 to the power 5 iterations, whereas the error here is like about 10,000, this is like 10 to the power minus 6. Okay, so practically, theoretically, this will also converge, but practically, this is this is much more useful. Okay, yes.
Can you explain so this part where exactly you use the linearity? So
Oh, so this is
I probably missed that.
so the linearity is kind of, so all of these expressions is because it's linear and you are having the contraction.
So is it only to kind of have this manageable expression here so that you have this ZT transpose kind of matrix showing up, or was there like even in the identification when you use the like the one thing is if you had stacking expectation y given x instead of gamma prime x, would things break down any place before this, or
Right.
this is the place where things start breaking?
No, so what happens is so here so in this model, for example, here you can allow this to be nonlinear. So it doesn't need to be linear technically, but this part needs to be linear because because here, as you can see, that if whatever error I have in this gamma star, let's say gamma t minus gamma star, so that becomes that kind of interacts in a linear manner with this, with the error in the theta t update. So let's say gamma t minus gamma star is the error in gamma t,
Right.
and theta t minus theta star is the error in theta t. So that interaction is kind of like a linear interaction.
Okay.
Whereas,
Okay, so that was my question. So if you had like, so the y given x part is linear, but if x given z part, if
Yeah,
was
that will work.
nonlinear, everything goes through.
everything goes through provided that you can show that gamma t converges to gamma star.
Yes. And I was asking that because in couple slides later, you have this ZT transpose showing up.
Yeah.
And I was saying was if you were using the kernel regression instead, the ZT prime would probably be replaced by the kernel matrix. So
Right.
the positive definition that you're looking for would.
Yeah, that will actually hold. Yeah, that's true. And like as long as it's like the underlying optimization is some kind of strongly convex function, basically the dynamics will be driven by the Hessian of that loss function, and that is positive definite. So any model which satisfies that should work. So, yeah.
But if your claim is true, like it doesn't matter whether y is linear or x is linear, it's just matter is entire error is whether controlled or not, right?
That is true. Yes. So if you can allow nonlinearity in y as well, but
Yeah.
you have to be able to control that.
Yeah.
I mean, of course, I mean there are some modifications possible where you show that you linearize and the nonlinear parts are becoming small over time.
Yeah.
That should work. But I mean, the crux of the matter is this. I mean, you need to have this. Yeah.
And one more thing.
Yeah.
About the positive definite simplification thing, like
Right.
isn't that term being positive definite isn't enough, because if it's too large, then it goes to.
But oh, right. That's a very good question actually. So you can control that by this alpha t plus 1.
Makes sense. Yeah.
Yeah. So So I'm assuming that you can make this small so that the maximum eigenvalue doesn't shoot up.
Yeah,
And
makes sense.
yeah. All right. So okay. So again, these are like pretty much standard assumptions, which is kind of close to like which is kind of similar to the previous setup. But the convergence rate is given by something like this, and here too, as you can see that this is the rate is kind of the order 1/t. And okay, all right. So this is the simulation setup. How much time do I have? 20 minutes. Okay. Okay, so this is a simulation setup. So for the first algorithm that we discussed, where we have two samples at each time point, and as you can see that these are like over various dimensions, but this is not very insightful. I would say is the only thing insightful here is that like as we move from like lower dimension to higher dimension, the error kind of increases and the variance also increases. So which is kind of expected that it will happen. And here the model is given by this phi gamma star z plus c. And as you can see that this, we are varying this c parameter over here, which controls the endogeneity between like the dependence of x and the error terms. Okay. But we do not have any data example for this particular algorithm. Why? Because we like most of the data do not appear in that manner. So it is possible to like illustrate our results probably if you have an offline data set, and for each zt, let's say zt is discrete like 0 and 1. So for each zt, you just sample 2 points xt and xt prime, and we could illustrate our results. But that doesn't like that's kind of like a fake kind of scenario where we are illustrating our algorithm. So data example for this doesn't exist simply because we do not have data like that, data collected in that manner. So I will move on to the performance of algorithm 2. Here again, there are too many things. So I will just draw your attention to a few points. Firstly, in this model, this row thing over here, this controls the endogeneity. And again, these are for like this is for dimension 1 and 1, and this is for dimension 8 and 16. And as you can see, we compare our methods. We compare both our methods, both like the algorithm which initially diverged, and also the method that we proposed later, the final algorithm 2. So we compare both of them with this. So this is the only work that we know of at least. So which implements this online 2SLS algorithm. But this approach requires a matrix inverse to be evaluated at every iteration. But since this is the only method, we compared our method with this one. So here, as you can see that as the dimension increases, and here the gap can be considerably large between the methods. But in the simulation setup, since this is a very vanilla simulation setup, the difference is not that evident. When we move to the data setup, as you can see here, so this is the data on children and their parents' labor supply data. This is a very like popular data set in econometrics. So here our response is number of working weeks of the parents, and X, that is the treatment or feature, whatever you would call it. So that the number of children is greater than 2. So it's a discrete thing. So it's 0 if it's less than 2, and more if greater than 2. And Z is first two siblings are of the same sex. So of course, this Z thing should be related with this one, because Z is of course related with X. But at the same time, whether you have first two siblings are of the same sex, that's completely random. And that shouldn't have to do anything with the number of working weeks if you remove the effect of X. Okay. And it doesn't depend on and it's clearly a random thing. So it doesn't depend on the error as well. Now, in this setup, as you can see that the final algorithm that we proposed, that converges faster, and at the same time, it kind of keeps on improving the estimate. Whereas the initial algorithm that we proposed and the other work, TVB23, both of them kind of converges slower and plateaus after some time. It doesn't improve the estimation anymore. Okay. So similar kind of behavior you can see in another data set. This is the Portland cement industry data. So here again, we are looking at this how many tons of cement has been shipped and what's the price. So this basically reflects that how price affects it. Yeah.
This data starts offline estimate is that parameters fitted from the entire data set.
Yes. Yes. So here, so Z is the wage of skilled workers, electricity price, coal price, gas price, and so on. So these are, of course, so it's kind of like unobserved confounders kind of thing. It's independent of epsilon. And theta star is the offline estimate of the data, because let's say we had the data in the beginning. So what's the estimate would have been, and how does our online method converges to that? Okay, this is just to illustrate the efficacy of our algorithm. And as you can see, in this case, both our algorithms kind of converge faster than this DPP23, and these gaps kind of remain like even after so many iterations, right? So in this particular case, the CSO updates that don't suffer that much from initial bad initialization, and it doesn't diverge. So here, this is a scenario where both of them converge at a pretty much same rate, because as gamma t gets closer to gamma star, both the iterates become very similar. Okay. All right. So these are the conclusions, and if okay, so I'll stop at this point, and so if you have any question before I move on to the next setup, I will take the questions now, or I can just move on to the next one. Any questions? Just selected this photo because this is one of my favorite photo at near San Francisco. It is at Martin's Beach. So this is like this. I took this about 4 or 5 years back. So better than awkward pause, I guess. So yeah. So if you don't have, yeah.
So for your data set that you analyzed, what aspect of it was streaming? Like,
so all the data sets that you are getting, all the data points that you are getting, these are, this data set.
yeah. So I mean, what aspect was like over time collected over time?
So yeah, so this is an offline data set. So we had the whole data set, but we are, so we assumed for the algorithm, we assumed that we don't have the data set and we just sample randomly from that data set. So if you had like, let's say 1 million data points, we just sample randomly from those 1 million data points. Okay. All right. So, looking towards future directions. So this is again like a recent photo from one of my trips. So I will concentrate on the first topic, which is learning with dwelling feedback. And this is a very famous duel. If you know, you know. If you don't, if you know, we'll be friends very soon. But if you don't know, probably we have to try harder. So yeah, okay. So this is learning with dwelling feedback. So here, what I mean is, so what is dwelling feedback? So dwelling feedback appears in so many different fields. The most prominent one in nowadays is ChatGPT, where ChatGPT provides you with different kinds of feedback, like different kinds of responses depending on what you asked, and it asks you which one do you like better, or if this is better than the other, and your answer is yes or no, right? But you do not really tell them how much. So because it's difficult to measure, I do not say that, okay, I like this 10 better than the other, or I hate this 5 worse than the other. I cannot say that. I just say whether I like it or not, right? Similarly, let's say you are in a doctor's office, you are in a psychiatric doctor's office, and so the doctor can only ask you, are you feeling better or not? If there is no way to measure how much better you are doing, really. So here again, this is yes, no questions, and there are so many different things, so many different scenarios where you just have yes, no kind of answers, right? And this is what I mean by dwelling feedback. So where you just know whether some option is better than the other or not. Okay. So here, if you look at it from regression point of view, so in regression, we know X, which is the feature, we know Y, which is the response, and we try to learn F, right? But in dwelling feedback, we just know whether F evaluated at X1 is smaller than F evaluated at X2. That's all. Okay. So we do not get to see the exact value of Y. All right. So is this system learnable? So for convex function, yes. If your loss function, let's say we are in the linear regression setup where the loss function is strongly convex, this is actually learnable, and you can solve this particular problem. But again, there are several challenges which remains. Firstly, in causal learning, there is, so if you think about DAG learning or IVER or like doubly Lobus learning and like all of these causal problems. So generally, again, we assume that we know why, but if you don't know why, this, even with why, it leads to a very challenging problem and leads to a very challenging optimization. But if you don't know why, then it's really open field, like what you can learn from it. And then there is question of multi-objective preference elicitation, which is basically ChatGPT. So what ChatGPT does, it thinks of various objectives that it needs to satisfy. And it kind of lets you know, like, like depending on those objectives and depending on your preference, it kind of tries to learn your preference over time. And how does it learn? Based on the yes, no answers that you have provided it, right? So similarly, you can think of problems where you are trying to sample from dwelling feedback in the sense that you do not know the exact posterior, but you just know the posterior, like whether the posterior, like the potential function of the posterior evaluated at one point is larger than the other. And yeah, so there are many different variations of these problems. So everything, like most of these problems are open, okay? Because this is fairly new in optimization literature, right? So here again, I should mention one thing. So there are a lot of works in statistics already on pairwise comparisons and learning from pairwise comparisons. But there, like in many of those problems, as you know, like let's say you form a loss function, you assume that you can solve it, and depending on that solution, the exact minimizer or maximizer, you kind of do your estimate. But how do you solve it? Because that itself is challenging, because you do not exactly know the function values, or you cannot exactly evaluate the gradient. Okay. So that's the major challenge. So next topic that I'm really interested in is how transformers learn, not this transformer. So yeah, so let me not this one either. So what I'm really trying to say is the real transformer that I'm interested in looks very dull. So this is what it looks like. So, and what does it do? So you know that there has been a lot of talk recently about the success that transformers see, and what's the major task that it has achieved success in is that why is it called transformer? Because you provide it with some examples or with some sentences in, let's say, French, and it converts it to English, right? It transforms the set of symbols that you have given it to another set of symbols. Okay, so it's a transformer, and the basic architecture looks something like this. So there is an input sequence, there is encoder, decoder, and there is the output. But of course, this is not the whole story. Then, like, you can write, for example, variational autoencoder also in a similar manner. But what's the main story? This encoder and decoders, they both have a self-attention layer and a feed-forward layer. And this self-attention is the major part for the success of transformers. Okay, so this is the major challenge, or this is the major innovation that led to this widespread success of transformers. Okay. Now, for this, I'm not going into the details of how these architectures are made. Let's say these are some modules which we have. Now, the major thing where transformers really excel is in context learning. So what is in context learning? So let's say I have a pre-trained transformer. So I do not really train the transformer. Somebody has given me a very nicely trained transformer or on some task. Let's say it is trained to convert French to English. Okay. Or it is trained to convert, let's say, yeah, it's French to English, or for example, Spanish to English, or something like that. Now, I will use this to translate English to French, or let's say, yeah, English to French. So this is my task. So what I will do is I'll provide it just some examples of it. Okay, so if sea otter, then this is the translation. If peppermint, this is the translation, and so on. Okay, I'll just provide it with some examples, and I denote these examples, or I represent these examples like this, that xi is the feature and yi is the response. So this is just a compact way of representing it, that's all. Okay, so this is just a t+1 matrix. So transformer knows that one by one these examples come in, and I just feed this input matrix to transformer. Okay, no training whatsoever. Even in that scenario, it can actually lead to if you feed after feeding some like examples, if you ask what the French of cheese is, it can provide you with a correct answer. Okay, so that's called in context learning, that I'm just learning in context. That means I am learning by the examples given to me without any training. Okay, so how is it different from supervised learning? So in normal supervised learning, regression, classification, what do you have? You are minimizing some expected loss where these data points are sampled from some distribution, and your loss function depends on the true function as well as your model, whatever you have predicted. So you want to learn the best theta, which minimizes this particular loss. Okay, and x1, fx1, these are the observed data points that you have fed into the model. So this is the typical setup. But now, if I talk about in context learning, then we have this setup which we already saw. But when I was saying that it's trained to learn from French to English or Spanish to English or something like that, that basically means that all these examples need not follow the same rule or same F by which it was generated. Okay, so it is probably something similar, but not exactly the same thing. Okay. And this prompt that I am generating, that can also be from unseen F even. I don't even know what the data generating mechanism is. I don't even have data from that. So if I translate these factors to this objective function, this is how it will change. Firstly, I have to be able to minimize this theta such that it minimizes the loss, not for only one data generating mechanism or only one F, but for over a distribution where F is sampled over this distribution over the function space. Okay, so it's here, the data is not only random, but the function itself can be random or sampled from a function space. Okay, and the other thing is that I provide it with several samples or several examples, and eventually I ask that what should be the corresponding output. So this xi is just cheese, and I ask it what should be the corresponding output. Okay, and the thing is that if I minimize this theta and if I take the output, my hope is that the output will be fxi. Okay, so yes.
If we write it that way, you're now considering the F in the first term and the F inside the transformer different as well, right?
Yes, sorry, yeah, this can be different. Yeah, sorry, yeah, this is like F1, F2, and yeah, that's a good catch. Yeah. Okay. So why does this work? Because this doesn't sound like this should work, but this works in practice. So why does this work at all? Okay. So if I look at just the linear model, so in typically what we do is we have a supervised, let's say we have a linear model by which y is generated, and we are trying to minimize this squared loss, this typical regression setup that we come across all the time. And in OLS, so what we do is we just get this W hat, which is the best least square estimate that you obtainable from this data set. And this works very nicely. It has very nice properties as long as W star is fixed, right? So we are assuming that the data is generated by some given W star or fixed W star, or in the Bayesian setting, it's just from a distribution. But we are trying to learn this W star by this, by this estimate over here. This is just the offline frequent estimate of W. Okay, W star. Now, if W star changes, if the data generating mechanism changes, then we need to again retrain the model or update our parameter estimate because our data set has changed and we need new data set to train our model. Okay. The other way to solve this problem is just to look at it from optimization perspective. And we just do the online gradient descent. By what I mean is that so here wi plus 1 is wi is my current estimate, and I generate the next estimate by this gradient descent step or SGD step. Okay, so I can do that, and that also converges to the same solution over here. Okay, so that's all very nice. But if I roll out this one, this is what it looks like, right? So as you can see, that starting from this initial point, whatever W1 was, I can, if by some manner, I can just arrange this, like I am getting one data point at a time, x1, x2, x3. If I can just calculate these terms or arrange this x1, x2 in this manner and just multiply with these factors to W1 and just evaluate these weights and just sum them up, let's say I am able to perform these basic operations, then that should also lead to W hat or W star. Okay. So question is, can a fixed model, by model here I mean like imagine a neural network or a transformer, can a fixed model implement gradient descent? By implementing, I mean that I will feed these examples or these samples to the model, and the output on the other end will be of this form. Okay, just by simple matrix manipulations, I will just push maybe one data point here. I'll just square them. Let's say the model is capable of doing all these basic calculations. So now, can I implement? If I can implement this with each example, then of course, or I can just implement this with each example, then of course I can have this W, the output on the other end should be something like this. Okay. Once I have enough number of samples, once I have fed enough number of samples to the model. Okay. And this is exactly what transformer does, at least in this setting. Okay. Of course, there are a lot of simplifications, and it's oversimplified setting as well. But this works good to illustrate what's happening. Okay. So transformers are able to do exactly this one. That means that given one data point, so this is what the main result looks like. So given one data point, it's capable of implementing a single step of gradient descent on that in context example, and it keeps doing that. And the output matrix kind of gives an estimate, something like this, after n data points. Okay. So this is what it looks like, and you can see that it's difficult to read here, but this green one over here, this is the OLS estimate, and as you can see, transformer trainings in both cases basically they converge to the OLS estimate provided by the closed form. Okay. All right, so this is just a vanilla setup, and this is already known. But what's the questions that remain? So there are a lot of questions actually. Firstly, so what happens for more complicated function class? Because it might not be the case that you just do gradient descent and it works for every possible scenario, but it works in many cases. So that's a good thing to remember. Secondly, so if I want, so instead of linear regression, if I just want a robust regression, if I just want to learn this robust regression parameter, is it able to do that? So there are so many other things like causal structure, or is self-attention at all necessary, or other is it transformers are of course expressive models because it has a lot of parameters and a lot of complicated architectures. But is self-attention really necessary? Like, can we theoretically show or prove that it is absolutely necessary to have that architecture, or do other complicated models can also have this property where they automatically learn the system just given in context examples? And how does in-context training performs from during the pre-training stage? Because so far we were assuming that the transformer is fixed. So what happens to ICL when you are training it actively? Okay, so how does that properties evolve for that? So there are a lot of different questions to be answered, and I think I already I'm over time, so I'll just skip over these parts. So these are this is another line of work where I work on this. As in the beginning, I mentioned that I work on inference of optimization algorithms. So again, there are different problems here. So if you're interested, we can probably catch up after my talk. And yeah, so and that's pretty much it. And thank you.
For this message and pull out and I hope everyone enjoy the break. See you next semester.
Thank you.
Thank you.